did you plot the line? So the logarithm of the molecular mass against the ratio between the elution volume and the void volume. What is the molecular mass you find? Did someone do this?
I found that the molecular mass is 251.
50?
251.
50 or 60, sorry.
51.
Okay, like
and 188.
or let's say 251 kilodalton, right?
Yeah.
You see, that. Okay. Does someone do the exercise? So normally you have to plot it. Let's see how this.
I have different answer.
Yes. Tell me.
The molecular weight is 319.
219?
300?
No, it's too high.
Okay.
When I plot, so the logarithm of the molecular mass against the ratio from the volume, I have obtained this graph. So you see my slide, right? Yes. So for me, from the equation here, and because we have a void volume of 30.3 milliliter, I found a molecular mass of 266 kilodalton. So it's quite similar than what you found, okay? So mind that the smaller protein will be elevate slower and the bigger, so that's why so the bigger protein will be eluded first. Bigger protein goes first, and the smaller elevate slower. Slower elution, okay? For the SDS page, this is the opposite of the gel electro exclusion gel, because this time the smaller protein go faster and the bigger goes slower, okay? So you normally have to plot the logarithm of the molecular mass against the distance of migration. We have an unknown protein here with a distance of migration protein X. Protein X is the unknown protein, okay? The distance of migration is 3.2 centimeter. So you should find the molecular mass of this protein. So if we plot this, let's plot properly. Okay. So normally you should find a line, okay, with this equation, and you should find the molecular mass. Could
So,
someone?
it's 35.4 and 35.5
You find
kilodalton. Yeah, I found
40 point
30, 35, 35.
35
Yeah,
point 4
yeah, 0.5 kilodalton.
kilodalton. Okay. And I found 40.8 kilodalton from my equation. Okay, but yes, it's quite the same. You should find something between, because it's here, the unknown protein, it's between these two distance of migration because it's 3.2 centimeter. So you should find something between 30 and 43. Correct? Do you have any question about the exercise?
Just I want to ask what is the unit of the unit of the molecular mass. Do we need to transfer it to kilodalton before we make the glucose, or we can keep the original unit?
You can keep it.
Yeah, okay.
Because in this equation, you will know that the y will be in kilodalton and the x in centimeter. Always use the same units.
Okay.
Okay.
Yeah. So in the exercise 10,
Yes.
so the original is Dalton. So we also keep this Dalton.
You can use Dalton or kilodalton. You should
Okay.
find the same line, but your equation will be different. That's all.
Yes. Okay. Thank you.
No problem. Another question or not? No question? Okay, let's start. About the exercise 9, it's okay for you? No problem. Okay. So I change. Je change.
Excuse me, I have one question on the exercise.
Yes, no problem.
So the two last one, the exercise 10 and exercise 11. If we have the test, can we use Excel to find the equation, or how do we have to calculate by hand? And how can we find the equation if we calculate by hand?
Now you don't have to calculate by hand. You can use Excel,
But
another software.
But like when we do the final test,
okay, you when you have a line, you don't know how to find the equation.
Yes,
this is mathematics. Okay, you have, so for example, you have to determine the slope and the intercept, right? The slope, you know how to do that? The slope of the line.
Yes,
it will be YB YA over XB XA. You can take 2 points. For example, A would be this, B will be this. Okay? For example, so in my example, you have to calculate the log of the mass. So logarithm.
Can you show slide? I cannot see your slide.
Sorry. Yes, because I didn't share it. You can see now? Yes. So for the slope here, you put 2 points. You put the logarithm, for example, of phosphorylase and beta alpha lactalbumin over the distance, so 1 minus 5.3. So this is the slope of the equation. Okay?
Yes.
And the intercept, how can we do that? But for example, you take 1 point. Now you have the slope. You can find the intercept, right? For example, if I take the example of phosphorylase beta, I will have log of 94 equal, I find the slope, so minus 9, so for 1, plus the intercept will, let's say, I, and after I can calculate, determine the I, and I have the equation. Okay?
Okay, thank you.
No problem. So let's share. Can you see the slide?
Yes.
Okay. Okay, so I will talk about two spectroscopy techniques, which are the absorption and the emission spectroscopy. And so here you have the electromagnetic spectrum and the electromagnetic spectra of an object, the characteristic distribution of electromagnetic radiation emitted or absorbed by the object. So when it will be emitted, it will be the emission spectroscopy. So it's the same as the fluorescence. And when the radiation will be absorbed by a molecule, it will be the absorption spectroscopy. So you should know some equation about the energy, the photon energy. So you have the energy, it's related to the wavelength, because we will speak about wavelengths. So this is wavelengths. Okay, usually we use the nanometer units. H is the Planck constant, and C is the speed of the light. Okay, so we can classify the electromagnetic radiation by wavelengths. So for us, we will use two of three regions. Let's see. Okay. Let's put here. We have the UV visible range. So it's between 200 to 800 nanometer. So let's say UV. UV. Oh, sorry. UV is from 200 to 400 nanometer. Visible. Visible, it will be from 400 to 800 nanometer. This is this region. And the last one is infrared. It will be from 800 to 4000 nanometer. Sorry, no. For the infrared, sorry, we use another unit, which is 400 to 4000, sorry, centimeter minus 1. This is the wave number, and this is the opposite of the wavelength. Okay. So here, so we will talk about UV visible spectroscopy, and it refers to the absorption spectroscopy in the UV visible region. That means that it uses light in the visible, and in this region of the electromagnetic spectrum, molecule undergoes electronic transition. Okay, so you have the ground state, and after, let's say, you have the first excited, sorry, here you have the ground state and the first excited state, and this state refers to the electronic transition. So this is electronic state, the ground and the excited state. So the absorption spectroscopy, you will have transition between the ground state and the excited states. Okay, so it refers to the green arrow. So the absorption spectroscopy is complementary to fluorescence spectroscopy. In the fluorescence spectroscopy, it is with transition, this time from the excitation state to the ground state. So it refers to the red arrow. Okay. When you have squiggly arrow, This means this one. It means that it's non-radiative transition. So here. Non-radiative transition. Okay, so when a molecule is excited by the light, the molecule will absorb the light and goes from the ground state to the excited state, so the green arrow, and after he will go back to the ground state by two ways. A non-radiative transition, it corresponds to the blue, yellow, and the violet arrow. So it means that the molecule is not fluorescent. And he can also go back to the ground state by emitting light. So it is the fluorescence, okay? And it corresponds to the red arrow. Okay, the fluorescence. So if you see the electronic state, for each electronic state, you have smaller state. It corresponds to the vibration state. Here, let's put another color. Here, it's the vibration state. And in the same way, you have the first ground vibration state, the first excited vibration state, and so on, the second, and so on. Okay? And you have to know that the fluorescence, it's only from the ground state of the vibrational state from the first excited electronic state. So it's from here to here, okay? So it means that the energy of the fluorescence, this is the length of the arrow, it's always shorter than the length of the, the energy of fluorescence is always shorter, lower than the energy absorbed. Okay? It means that if you see, if you compare the emission the absorption here, spectra, and the emission spectra, so this is the light against the wavelength. The emission spectra is always on the right side of the absorption spectra, because here you have lower energy and here higher energy. Okay, because you have the energy is inversely proportional to the wavelengths. Okay, we call the Stokes shift. The Stokes shift is the difference between the maximum of the emission and the absorption spectra. Okay. In our case, the case of proteins, only the aromatic amino acid contain delocalized p electron and then strongly absorb the UV light. So only tryptophan, tyrosine, and phenylalanine can absorb in the UV region. Okay, no other amino acid absorb. So you know the Beer-Lambert law, sorry. So you have the emission intensity of light, or I0, and the absorbed light, transmitted light. So we can have the absorption is minus log of the transmitted intensity of light the intensity of the incidence light, and it is proportional with the concentration. Okay, so the absorption is without unit. C, the unit of C will be gram per mole. L correspond to, it's in centimeter, and it corresponds to the light through which the light passes. Usually it's 1 centimeter, and the epsilon is the absorption coefficient, and the unit of this, it will be it's the concentration, so it's mole per liter. So the absorption coefficient, the unit of the absorption coefficient will be molar minus 1, liter, and centimeter minus 1. Okay. So usually a protein has a maximum of absorption at 280 nanometer because of the absorption of tryptophan. It has a higher absorption coefficient. So you will have always a protein with an absorption at 280. Okay, the absorption coefficient is proportional to the molecular mass of the protein because it's proportional to the number of tryptophan usually. Okay, so you see that this absorption coefficient increase from here to here with the size of your molecular mass of your proteins. Okay, so the absorption coefficient is less or more proportional to the molar mass of the protein. So remind that always the maximum of the protein is 280 nanometer because of the tryptophan, because of all the aromatic residue. Now, if we see the fluorescence, so you have here the absorption spectra of tryptophan, tyrosine, and phenylalanine. So you see that the absorption of tyrosine is higher than the other. And if we see the emission, this time, the emission spectra of this amino acid, you will have an emission of tryptophan and tyrosine higher than that of phenylalanine. Okay, so in the article, when we talk about intrinsic fluorescence, it means that we talk about tryptophan fluorescence. So the tryptophan fluorescence, you will have an emission spectra of the protein. It will be usually between 300 to 500 nanometer. Okay, so this is this part of the spectrum. So this part of the spectrum, okay? And to have this emission spectra of your protein, the excitation wavelengths always correspond to the maximum of wave, the maximum with the maximum wavelength in the absorption. Okay, so we know that the maximum wavelength in the absorption spectra of a protein is 280. So the excitation wavelength to have an emission spectra of a protein, it's always 280 nanometer, and it corresponds to the absorption of the aromatic residue. And it's, for instance, it's a very sensitive techniques, and we can have information about the nature of the environment of the protein and especially of the tryptophan. So typically when we perform experiment with denaturant, surfactant, or other molecule, or for example, if we increase the temperature of the solution, we will have a change in the emission spectrum. Okay, because the fluorescence it's very sensitive to all this. So the temperature, the pH, the hydrogen bond, the presence of ion, and the presence of also denaturant. And also it's very sensitive to the polarity of the solution. Okay, so if you increase the polarity of the environment around tryptophan, you will observe what we call redshift. And in this way, it's called the blue shift. Okay, we will have an exercise, but I want to explain that because maybe you have not understood. So it's called a solvatochromic. So it depends on the polarity in the polarity of the environment. So tell me, tryptophan is it an hydrophobic or hydrophilic amino acid? Because when we study fluorescence, intrinsic fluorescence of the protein, we study the fluorescence of tryptophan. So is it hydrophobic or hydrophilic? So are you there?
Yes. I think it
So my
is hydrophobic.
Okay, so tryptophan is hydrophobic. So it will be inside the protein or rather outside.
It's going to be inside.
Inside, correct? Because if you have a soluble proteins, it will be surrounded by water. And so the tryptophan, because it's hydrophobic, should avoid water and will be inside. Okay? When you perform experiment in the presence of denaturant or when you increase the temperature, what happens? Your protein will be unfold. It means that you have the change, you have your protein, okay, the peptide change, and when you increase the temperature or use the naturant, you will have only one line, okay? So this is the native protein and the unfold protein, right? We said that tryptophan should be inside because it's hydrophobic, but when you have the unfold protein, the tryptophan will be there. So in the beginning, in the native state of your protein, the tryptophan is not surrounded by water, right? And when you have the unfold protein, the tryptophan will be surrounded by water. It means that the environment of the tryptophan becomes more polar because you know that the water is a polar solvent. Okay, so you will observe a red shift from the emission spectra when you increase the temperature, when you come from the native protein to the unfold protein. Understood or not? We will see that in an exercise just after. Do you mean, shall I repeat again? Or
Can you repeat the part when the protein is unfold and it becomes more polar?
okay. So here you have, when it's native, you have the plot, the red plot. I draw that. It's water, okay? So it means that the tryptophan in orange is not surrounded by water, correct? When we increase the temperature, for example, we will have from a native state of the protein to the unfold protein. If you have the unfold protein, it means that now the tryptophan is surrounded by water, okay? It means that the environment of the tryptophan becomes more polar because water is polar. So you will observe a redshift in the emission spectra. For example, if we have this, for example, let's say that this spectra is the native spectra of the proteins, okay? When you will have an unfold proteins, you will observe a redshift. That means that you will have, for example, something like that. It means that the maximum of emission is higher in the wavelength, so you have a redshift. So here it's an unfold protein. Okay? So let's see the exercise. Does that mean when tryptophan exposed to solvent, tryptophan will emit? Yes, you're correct. When tryptophan is exposed to water, tryptophan will emit fluorescence with a higher wavelengths. Is it correct?
Why?
Because when you increase the polarity, you should observe a redshift. And you know that water is a polar solvent, right? So it means that tryptophan, when it's unfold, is exposed to water, or it's around to water. You see that there are more water around the tryptophan, so you will observe a redshift.
I mean, the fact that tryptophan will emit a higher emission wavelength when exposed to a higher polarity environment, that is a characteristic of tryptophan, or is there something that I didn't
No, it's
catch?
characteristic because the emission of a protein, it's related to tryptophan because it's only amino acid which have a fluorescence. Okay, so when we talk about fluorescence of a protein, it means that we look at the fluorescence of the tryptophan. But if you have another molecules, for example, organic molecule, you will observe the same redshift when you change the solvent. For example, if you have a molecule in benzene, which is an apolar solvent, and you record the same, the emission spectrum of the same molecule, but this time in water, you should observe a redshift in the emission because you increase the polarity of the solvent.
So the increase in the increase in emission wavelength always happen when the polarity increases.
Yes.
Okay, I understand. Thank you.
And we will see an example. When you have aggregation, it means that you avoid the water. You will observe a blue shift this time because you decrease this time the polarity. Okay? So let's try to do an exercise about emission, absorption and emission. So I think you probably use these techniques to measure the concentration of your protein. Is it the Bradford method? Do you have practical class? No? Okay. But I think if you work in a lab, you should probably do this. So it's called the Bradford method. It's a biochemical assay for determining the total level of protein in a solution. It means the concentration of all the protein in a solution. And we use a dye, which is called Comasy Ryan Blue. Okay, this is the dye.
I'm sorry, your slide is not clear.
You cannot see the side. Sorry,
Yes.
I forgot to share. Okay. So it's more easy to work in the visible region than in the UV region. That's why we use a dye, because proteins, it's usually on color. That's why we use a dye called the Comasy Blue to measure the concentration of the protein in a solution. Okay, so we have an interaction between proteins and Comasy Blue, and the solution becomes blue, and we have an absorption at 585 nanometer. The amount of protein in the sample can be estimated by reading the absorption at this wavelength of the end product of the Comasy Blue reaction. Indeed, we need before to plot a standard curve of a select standard protein, which is usually BSA, so it's bovine, serum, albumin. Okay, so given the structure of the Comasy Blue, which interaction occurs between Comasy Blue and proteins? So in this molecule, you have different regions, okay? Here you have ionic part, here cationic, okay? So if you have ion, you can have what kind of interaction? Electrostatic interaction, right? What kind of interaction you can have also? Can we have hydrophobic interaction? Hydrogen bond? Do you understand my question? Hello.
I think we can have hydrophobic interaction.
Okay. With which part of the protein of the Comasy Blue?
The right.
With the aromatic ring.
Yes.
Okay, so each time you have an aromatic ring like this, you will have hydrophobic interaction. Okay, and the last one, hydrogen bond. Can we have some hydrogen bond?
Maybe
With, okay, with which function or which part of the proteins?
on the left.
On the left, this part, yes. Each time we have an azote or an hydrogen linked to an azote, an oxygen, hydrogen linked to an oxygen, which is the case here, and here you have a nitrogen. Okay, so with this function in red, you can have hydrogen. Okay. After, so we have to plot the standard curve. Okay, so what we use BSA at this concentration, and we mixed the BSA with the Comasi blue, and we have this absorption at 595 nanometer. Okay, so trace the standard curve and tell me if this technique is correct at all concentration. And after, you have to give me the equation of the standard curve. Okay, so you can use your computer and whatever software you want, and you have to explain, tell me what is the concentration of the unknown proteins. Okay. I give you 5 minutes. Let's say 10. Do you have any question about this? You know what to do? You have to plot the absorption at 595 nanometer against the concentration of BSA. Okay. So you will plot this. And you should tell me if you have a line or not. So you find, yes, so what is the concentration of your unknown protein? So if you plot the absorption against the concentration, you will have this dot, okay? And you see that at the beginning it's linear. That means that the absorption is proportional to the concentration, but at the end it's not linear. Okay, it's not in the same line. The last 2 points. Indeed, the Beer-Lambert law, it's not correct for all the concentration. Okay, why? Because sometimes when you increase the concentration of your protein, what happens? You can have dimerization. And here you, at the beginning, so at low concentration, you have monomer. So the monomer and the dimer are not the same species. So it means that the absorption coefficient, it's not the same. So the Beer-Lambert law is not correct for all the concentration. That's why we need to plot the standard curve to be sure to be in the region where the Beer-Lambert law is correct. Okay, and so we have this equation from this plot. So it's quite yes, it's quite the same that what we tell me in the chat. Okay, and so from this equation, it means what is the slope of this equation? It corresponds to the absorption coefficient, right? So the absorption coefficient is 9.41, 10 minus 4, and the unit will be microgram minus 1 because the concentration of BSA it's microgram milliliter, and centimeter minus 1. Okay? So with the unknown, so you have the absorption, which go to the epsilon LC, and the unknown protein has an absorption of 0.269. So its concentration it's equal to 0. So did you find the concentration of the unknown? I find 285.8 microgram by milliliter. Okay?
Okay.
Do you have any question?
I have a question.
Yes.
So when I use Excel and I type in all those numbers, then I build the chart, and use the Excel tool to form a trend line, and it doesn't.
But you have to select only the first 5 plot dot. You have to remove from the Excel the 2 last point.
So you did that like manually, or?
Yeah. Yes, I did with Excel, and I asked to Excel that the intercept should be 0. Let's see. Can you see my Excel sheet?
Yes,
Okay.
I can see it now.
Okay, so I select the 5 point. Okay, I go to add it's in French. So add a curve. So it's linear, and I define the intercept to 0. It means I force Excel to plot the line and to have this point 0 and 0. Okay. So I will have this, but I would change the police and I will get the scientific. It's okay. I'm sorry, by Zoom, it's very difficult to show you. Usually,
it's okay. I can kind of see, but like, because I wasn't sure whether which point is it lies on that standard
yes,
curve
I
and which
understand.
doesn't. So like I didn't know which one to like exclude from the data and from the trend line.
Yes, because if you plot all the line which goes for all the plot, for example, you will have another equation, and if you draw, sorry. No, sorry. So you will have another equation, and you will probably find another concentration. Okay, but it's just to show you that indeed you should know that the Beer-Lambert law is not correct for all the concentration. So you have to choose the point which gives you the best line indeed. Okay? Okay. So let's take 10 minutes of break, and after I will continue the lecture. Okay? See you in 10 minutes. Shit. Let's go. So now I will talk for the last two lecture about the protein and the primary, secondary, tertiary, and quaternary structure of the proteins. Indeed, conceptually, protein structure can be considered at 4 levels. So the primary structure include all the covalent bonds between amino acids, and it's normally defined by the sequence. So the primary structure, it's the sequence, so we know how to determine the sequence by the element degradation and by the peptide overlap techniques. And so you have the covalent bond between amino acid and also the location of disulfide bond, okay, sequence plus disulfide bond. Okay, the relative special arrangement of the linked amino acid is not specified. The polypeptide chains are not free to take up any three-dimensional structure at random because you have steric constraint, and many weak interaction stipulate that some arrangement will be no more stable than the other. We know the weak interaction, which are hydrogen bond, hydrophobic interaction, and ionic interaction. And you know that the hydrogen bond is very directional. So the secondary structure refer to regular recurring arrangement in space of adjacent amino acid in the polypeptide chain. And we will see there a few common type of secondary structure. And you probably know that the alpha helix and the beta conformation, we will see these two secondary structures. So this is the local folding of the polypeptide chain. And for example, you will see the alpha helix and the beta sheet. The tertiary structure refers to the spatial relationship between all amino acids in the polypeptide. So it's the complete three-dimensional structure of a large protein. Okay, if your protein have several polypeptide chains, you can have more than another level of structure, quaternary, which is called quaternary structure, so which refer to the spatial relationship of the polypeptide or subunit within the proteins. Okay, so all the proteins have primary, secondary, and tertiary structure. Some other protein can have another level, which is the quaternary structure, if the protein possesses several polypeptide chains. Okay, if the protein is only a monomer, it means that he has only one polypeptide chain. He cannot have quaternary structure. Okay. So, if we remember the structure of the peptide bond, this is here, the peptide bond. You have the C alpha, the double bond between the C and the O, and the nitrogen and the other C alpha. And you remember you have delocalization of the p electron in the polypeptide bond. You can have a delocalization of the p electron. So I told you then that you have a plane composed by the two C alpha, the N, nitrogen, hydrogen, the C, and the O. all these atoms all these 6 atoms are in the same plane. Okay? So the backbone of polypeptide chain can be pictured as a series of rigid planes. So you have several rigid planes. Separate by substitute methylene groups. Okay, so you have a carbon here and you have a plane which can be with a different angle between the plane. So rotation is permitted about the N and the C alpha, and the angle of rotation is called C, phi. And it's also the rotation is also permitted between the C alpha and the C bond, this bond. And the angle of rotation, it's called psi. So here you have here is phi, and this is psi. Okay? And by convention, both phi and psi are defined as 0. So this is the convention. So the phi is for the rotation between N and C alpha. The phi is for the rotation between the C alpha and the C. And by convention, the 0, 0 corresponds to this conformation. So this is this point. This point corresponds to this conformation. Okay? So you can see in this conformation is not allowed because you have steric constraint between the hydrogen and the oxygen. Okay, so the Ramachandran plot, it's the plot between the phi and the psi. And there we have, so it's all the phi and the psi observed in the protein. Okay? And in the white region, it's not allowed. It's a conformation not observed, not allowed because of the steric constraint, like this constraint. In the green region, dark green and also light green, this is the conformation which are observed in the protein. Okay, so the Ramachandran plot shows the conformation permitted for most amino acid residue. Okay, so should I write? So in white, not allowed. And in green, observe or permitted in protein. Okay?
Not allowed for the protein.
Oh, it's because you have a steric constraint.
Okay.
So it means that you will have you will have van der Waals. If you see the van der Waals radius of each atom, for example, for the 0, 0, which is not allowed, an unallowed conformation, you have steric constraint between the H and the O. It's two Okay, it would be repulsive interaction between these two atoms because you will have the van der Waals radius. Okay,
Okay.
so you have only few permitted region, only the green one. Okay.
Okay.
So let's start by the alpha helix. So this is the first secondary structure found in the protein. That's why it's called alpha. And the second will be called beta. Okay. So the first one is alpha. It is found by Pauling. Who received a Nobel Prize in chemistry. Nobel Prize in 1954. Okay, so this is the structure of the alpha helix. So in the alpha helix, you have hydrogen bond between the CO of the I amino acid and the hydrogen of the amide bond in the I+4 amino acid. Okay. So this alpha helix is the rod-like structure because you have for each amino acid the hydrogen bond between the CO and the NH. And what you should know about this alpha helix. So first, sorry. By term, you have 3.6 amino acid. Okay, by term, you have 6.6 amino acid. It means that if we have a top view of your helix, top view, if you have the amino acid 1 and the amino acid 2, I have an angle here of 100 degrees because I have one turn, it will be 360 degrees. I have 3.6 amino acid by turn, so the angle between two adjacent amino acids will be 100 degrees. Okay, the pitch of the alpha helix is 5.4 angstrom. So it's a high of one turn. Okay, this is the same here. You have the same here. Do you know what is an angstrom? 1 angstrom. It's 10 minus 10 meter. So it's 0.1 nanometer. Okay? Is it okay? So here you have also a top view of your helix. And you can see the side change in violet. The side change of each amino acid. It means that all the side change of the amino acid are outside the helix. Okay, and it will be very important because we can have interaction between the side chain of each amino acid, and we can have interaction between the alpha helix. Okay. Usually, the screw census of an helix is right hand. But so the most frequent alpha helix is right hand. And so it's clockwise if you know you want. But you have sometimes left hand amino acid. Okay. If we take all the alpha helix, the data about all the alpha helix, the average, an alpha helix contains around 12 amino acids. Okay? But it means that you can have more than 12 amino acids. You can have 50 amino acids for the high alpha helix. 12 amino acids, it corresponds to approximately 3 turns. So you will have approximately a length of 18 angstrom. This is the average data about alpha helix. Okay. So an example about alpha helix. So it's found in keratin. So keratin refers to a family of fibrous structural proteins. So it's the key structural material making up the outer layer of human skin. So you have keratin in hair, in nail, and keratin monomer assembled into buckle to form filament. Okay, indeed, keratin, you have this sequence with A and D, which are apolar residue. And I told you, if the first amino acid is A, the B1 will be at 100 degrees. Yeah, the angle between A and B is 100 degrees. No? It's the top view. After that, between B and C, you will have also 100 degrees, and between C and D, 100 degrees. Okay, so it means that on this side of the first alpha helix, you have apolar residue. In the second alpha helix, you have also A, B, C, and D. It means that you will have also the apolar residue in the side of the alpha helix. So what interaction can we have between this apolar residue? It will be hydrophobic interaction. Okay, so you will have alpha helix, several alpha helix with hydrophobic interaction between A and D. And after, these keratin molecules will form a very stable helix like this. It's several alpha helix in interaction, okay? And you will have a super core. Okay, so you will have multimer, and depending on the number of keratin, you will have something strong like nail and something less strong, for example, hair. In keratin, you have, in addition of this hydrophobic interaction, you can have also disulfide bridge. So disulfide bridge, it will be between two cysteine. Okay. So for example, human hair. In general, you have 14% of cysteine. Okay, and so with this covalent bond, because disulfide bridge is covalent bond, you can that confer additional strength and rigidity in the human hair. Okay, and you know, with Asian hair, Vietnamese hair, if you want to have wavy hair, what can you do? You will reduce the disulfide bridge by using reducing agent or by burning your hair. Okay, and you will create another disulfide bridge between the cysteine to have wavy hair. Okay, so the more flexible and elastic keratin of hair have fewer disulfide bridge than the keratin in mammalian fingernail, for example. Okay, so the more flexible, the less disulfide bridge you have. Okay. If you have questions, tell me, because I cannot see your face and I cannot see if you understand. Okay, so this is the resume, the sum up of what I told you. So you have the keratin with two apolar residue, which is rich in cysteine. So first you have the secondary structure of keratin, which are helix. You will have hydrophobic interaction and have superhelix. So you have a core between the alpha helix. And after you will have cysteine. So disulfide bridge between the different superhelix. And so you will have a protofiber. Okay. And what I told you about the wavy hair. So when you want to change your hair, what you will reduce the disulfide bridge, curl to have wavy hair, and oxidize to create new disulfide bridge and to have your hair like you want. No question about the alpha helix? So the alpha helix in the Ramachandran plot correspond to this region. Okay, we will see now the beta conformation, so the beta sheet. So I told you the beta, it's because it's a secondary structure discovered. Okay, so here, for the beta sheet, hydrogen bonds are between adjacent polypeptide chains. Okay, you have several chains. And now you have hydrogen bond between adjacent polypeptide chains. And it's a different way for the alpha helix because it was the same chain. Okay. You can have parallel sheet. It means that the direction of the peptide from the N to the C is parallel, like the top of the figure. Or you can have anti-parallel sheet. It means that the polypeptide change goes from the N and C, and after the N and C from the left to the right, and after from the right to the left. Okay? And you have the hydrogen bond between the CO and the NH, nitrogen and H. Okay? Yeah. Do you remember what I told you about hydrogen bond? In your opinion, in which case you have the stronger hydrogen bond? In the parallel sheet or in the anti-parallel sheet?
It's an anti-parallel sheet.
Yes, why?
Because the bond is strained.
Yes.
Yeah.
Yes, correct. I told you when I told you I discussed about hydrogen bond that the hydrogen bond is stronger when the 4 atoms involved in the hydrogen bond are in the same line. Okay? Here you have the nitrogen, hydrogen, oxygen, and the carbon. Yes, in the same line. So it means that the hydrogen bond is stronger. Okay, so this anti-parallel sheet has stronger interaction. Okay, so one polypeptide involved in a beta sheet, it's called a sheet. Okay, oh, sorry. This is one sheet. And when you have interaction between several sheets, you have what we call, sorry, I confused. This is a beta strand, sorry, and this, so one change is referred to a beta strand, and when you have several beta strands in interaction, it is called beta sheet. Okay, so for the average beta sheet, usually you have 6 amino acid in the beta strand and 6 beta strand for one beta sheet. This is the average. Okay. So for 6 amino acid in a beta strand, it corresponds to a length of 15 angstroms, approximately. Okay, so we have the beta sheet here with the hydrogen bond. So it will form, the sheet will we can consider the sheet as a plane. Okay, so this is the side view of the plane here, side view. Okay, So in the side view of the chain, you have what you have. You have the side change of the first amino acid here. And for the second amino acid, the side change is on the other side of the plane. Okay, you can consider this as a plane. Maybe we cannot see. Okay, so you have the first on the top, the second on the bottom, the third on the top, and the fourth on the bottom. Okay, that is also. So you have alternatively up, down, up, down. Okay, and the side change are perpendicular to the sheet plan. It's very important because if we see the structure of the silk, it's, you have this sequence, glycine, serine, glycine, alanine, glycine, alanine. It means that you have a polypeptide which are rich in glycine and alanine. Glycine and alanine are apolar residue. Okay, and if you see the side view of silk, what you have layer of anti-parallel beta sheet. You have one sheet here, another sheet here. You have the string here, another string here. So two string compose sheet, and two sheet is one of the structure of the silk. You have here a side view also with all the sheet of the silk. And what we have, you have the alanine here, and you can have so hydrophobic interaction between the alanine of each sheet. Okay, so you have the alanine here and here and here. Question about the beta sheet? No. A third secondary structure, it's a beta term. Okay, why? Because you have globular protein usually, and because you have anti-parallel sheet, you should have a change, a polypeptide change between the first strain and the second. Okay, and here also. So you will have beta term between these different strains. So in the beta term, you have a nitrogen bond always between the NH and the CO. So the CO of the first amino acid and the NH of the fourth amino acid. Okay, so you have beta term often found where the polypeptide change abruptly reverse direction as in the beta sheet. So here you have a table with all amino acid. You have the amino acid and their frequency in the secondary structure. So in the alpha helix, in the beta sheet, and in the term. So here you have the, in yellow, the hydrophilic amino acid, which is involved in the alpha helix usually. The bulky, so it's in French. This is bulky, hydrophilic. You can bulky amino acid, so large amino acid, which is usually involved in the beta sheet. And you have also two particular amino acid, which is glycine because it's very small, and proline because you have a secondary amine function. It's so usually when you have glycine and proline, you have a beta term. Okay. Okay. Now we can see two techniques to study the secondary structure of the proteins. The first technique is the infrared spectroscopy, and I remind you. So infrared, it's between 400 to 5,000 centimeter minus 1, okay? And you have the characteristic infrared band of the peptide linkage. So you have several bonds in the peptide bond. So the most important one are the amide bond. Okay, and it corresponds this region, which is the most important. Let's say this region, which corresponds to the amide 1, it corresponds to the CO stretching. Okay, so here you have the infrared spectrum of a protein. You have this different band which are correspond to, for amide 1, the NH stretching, amide 3 here the CN stretching, but for us we will focus on this amide 1 bond which corresponds to the CO stretching, and it's around 1060 to 1600 to 1700. And so we focus on this band, and depending on the secondary structure, we will have several bands. Okay, so alpha helix, for example, correspond to this wave number. The beta sheet corresponds to this wave number, and so on. And you have also unordered conformation. So usually you have only one band for the amide 1 band, but with the computer, with mathematic treatment, so you can make a deconvolution of this band, okay, and you can have several bands, okay, and always with the help of software and the computer, you can have the percentage of each secondary structure. For example, in this example, you have a band at 1621, which corresponds to a beta sheet. Okay, you measure the air under this band, so you have two bands here, and it corresponds to half of the protein. So half of this protein is composed with beta sheet. You have a band at 1650 here, which corresponds to the alpha helix, and the computer can give you the percentage of alpha helix in this protein. So it's 50%. You have 60% of disorder conformation, and you have 22% of turn. Okay, because you have a high percentage of beta sheet, you will have a high percentage of turn. One problem to record the infrared spectra that usually you use water as a solvent because your proteins are soluble in water. And if you see the infrared spectra of water, what you have an absorption of water in the same region of amide 1. It means that the infrared spectra of water will hide the amide bond. Okay, so what we do, we record the infrared spectra of the protein in D2O and not in H2O. D, you know what is it? Is the isotope of hydrogen. It's a deuterium, right? And this time, this band is shifted to another region, and you have here the transparency window. And now you can record your infrared spectra of your protein, and you will see the amide 1 band in this region because it's a transparency window. Okay. The second technique to study secondary structure is the circular dichroism. This time we use we use light in the UV near UV region. It means that we will record the spectra between 180 to 250 nanometer. Okay. And we will use left and right circularly polarized light. And because you have proteins which are composed with chiral amino acid, you remember the amino acid which the protein are composed with amino acid which is in L configuration and not DL. So you will have a difference in the spectra when you will use right or left circularly polarized light. So just learn this kind of spectra. You will record the difference between the spectra with the light and the left circularly polarized light. And you will observe this kind of spectra, okay? So between 180 and 250 nanometer. And depending on the secondary structure, you will have several spectra. So it's typical, okay? So for example, for the alpha helix, you have the black spectra. So you have in the alpha helix always two minimum. That's the way to recognize an alpha helix. You have two minimum in the region of 200 nanometer and one maximum in the near ultraviolet region. For the beta sheet, you have only one minimum and one maximum. Okay? And for the unordered conformation or random pole, you have the opposite spectra of the beta sheet. It means you have first a maximum and after a minimum. Okay? So we will think. Yes.
We always use both left and right circular line, or we will choose.
Sorry, I didn't. You have.
I want to ask, like, because we have the left and right circularly polarized. So in your
Yes.
experiment, we will use both type of line, or you only one.
No, because you will record the spectra of the left light and after the right light, and you will measure the difference between the absorption, okay, between the left and the right.
Okay.
And you will observe this kind of difference. That's why you have negative absorption. Normally, you should not have negative absorption. Okay?
Yes. Yeah. Okay.
But just, I don't care how to do this spectra, just remind the spectral region, it's the UV region, and the shape of the curve, okay? You should remind that if the protein is composed with most alpha helix, you should observe two minimum and one maximum, and so on. Because when you record a CD spectra, you will use software and computer, and they will calculate the percentage of alpha helix and the beta sheet. Okay? No question? So we will finish with exercise. Where is mine? So you can read the exercise 14. We have a peptide with this sequence. First question, very simple. Which amino acid is in the N and the C side of the chain? So you should know that. The N side is on the left or on the right?
On the left.
N on the left, yes, and C on the right, correct. Imagine this peptide falls as an alpha helix. What can you say about the orientation of the charged amino acid and the upper residue? Okay. So you have a top view of an helix here. So if I put the valine here, so each angle it's 20 degrees. Okay, so I know that the glycine, what is the angle between the valine, the first and the second amino acid?
100.
100, so it corresponds to 5 angles. Okay, so if I put the valine here, glycine will be here. Okay, and so I continue. I will have glycine, glutamate, alanine, glycine here, aspartate, aspartate again, valine, and blue. Okay, I will put the number. Okay, so it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. It's okay? Do you understand what I did? So,
No, can you explain again how can you write like that?
okay. I told you in my lecture that in the alpha helix, the angle between the first amino acid and the second one in the alpha helix, it's 100 degrees. Okay? So if I plot the valine on the top, I will have between the first and the second, here in green, an angle of 100 degrees. Okay? And between the second and the third, also an angle of 100 degrees. Okay? Each time you have 100 degrees. Understood?
Yes.
Yes.
Okay. So I plot all the amino acids of this sequence. And if I have the top view of my alpha helix, I have this. So where are the charged amino acids? So in this sequence, valine, it's polar or apolar?
Polar.
Apolar, hydrophobic, right?
Yes.
Glycine, hydrophobic. I cannot hear you, sorry.
I say I'm polar.
Apolar, okay. Glycine. You see that all the apolar, and you have also alanine, are in the same side of the alpha helix. Okay? If we take aspartate, glutamate, and aspartate, this amino acid are this time polar or not polar? In violet,
It's polar.
it's polar. It's indeed charged. More than polar is charged amino acid. Okay? You remember? Do you remember
Yes,
how we call a molecule which has a part which is charged or polar and another part which are hydrophobic? Maybe you don't remember that, but
Amphiphilic?
yes, correct. It's amphiphilic or amphibatic as you want. Okay, helix. So it means that you can have interaction between several helix. Okay, you can have ionic interaction with this part of this protein, ionic or polar or H-bond interaction with, for example, another alpha helix. And you can have hydrophobic interaction with this side of the alpha helix. Okay? Question about that?
No, I don't have any question for this exercise.
Thank you to answer. Second part of this exercise. You have this sequence. These proteins form a stable secondary structure, so you have to tell me which structure. And sorry, maybe it's better like this. And you have, they tell us that this protein can form a dimer at concentration. Okay, the isolate monomer can interact with membrane, so it means that he possesses a hydrophobic part, but the membrane cannot, the dimer cannot interact with the membrane. It means that the dimer has no hydrophobic surface. Okay, so you have to propose for this protein a secondary structure for the monomer and the dimer. So we have to tell me which amino acid are hydrophobic. Okay, I will put the amino acid in violet. Alanine, is it hydrophobic or not?
It's hydrophobic.
Okay. Arginine? No.
Hydrophilic?
Yes. Valine? Hydrophobic. Okay. Methionine, hydrophobic. is a leucine also, alanine also, lysine also. Tryptophan is hydrophobic, ND and D. After we have methionine, lysine, alanine, phenylalanine, alanine, valine, and leucine. So in violet is the hydrophobic amino acid. Okay. In red, let's say red, you have polar amino acid. Serine is polar, it can make hydrogen bond. Lysine is positively charged. Glutamate is negatively charged. Lysine. Aspartate is polar. Threonine were a hydroxyl group, so it can make hydrogen bond. As glutamine, threonine, aspartate, and so on. Okay. So you have in this sequence, alternatively, an hydrophobic amino acid and a polar amino acid. Okay, and you have gly. I told you that the presence of glycine is usually due to a beta term. So here you will have a beta term. And so if you have a beta term, it means usually that you will have a beta sheet. Beta term here, a beta strain here. So the whole, it's a beta sheet, okay? So
Wait, can you repeat that? I just lost
sorry.
connection for a little bit. I didn't know why there's a beta turn. Is it because like the two
beta term? The beta term is because you have in my lecture you have a table and with the amino acid and the frequency of this amino acid in the secondary structure. And I told you that when you have glycine and proline, usually it's because you have a beta term. Okay? So probably this part of these proteins is a beta term. Okay? And you have also alternatively the hydrophobic amino acid and the polar amino acid. And you remember when you have a side view of your sheet, you have the first side chain on the top and the second side chain on the bottom. Sorry. And in our case, we have, so, sorry. In our case, we have a side which is hydrophilic because it's polar amino acid, and you have another side of your beta sheet which will be hydrophobic. Okay, this is a top view, a side view, sorry. Of the sheet. So you have two strings connected by a beta term, and so it forms a beta sheet. One side of the sheet is hydrophobic, and the other side of the sheet is hydrophilic. Okay, because you have alternatively hydrophobic and polar residue. Okay, so it means that in the dimer, you can have in the dimer, if I draw the dimer, I can have hydrophobic interaction between the two monomers, or I can have hydrophobic interaction. Okay, so hydrophobic interaction. And in the other case, hydrophilic interaction, it means ionic interaction or H bond. Okay. Okay. So in my dimer, in my monomer, I have a hydrophobic side, which is in violet. And the other side, it's composed with only polar amino acid. Okay. So if I have hydrophilic interaction between the two monomers, it means that at the surface of my monomer, or my dimer, I will have amino acid at the surface, which are hydrophobic. If I have hydrophobic interaction between two monomers, the dimer will have at its surface polar residue. Okay? Which dimer can interact with the membrane and which one cannot? Because we are looking for a dimer which cannot interact with membrane. It means which cannot have hydrophobic interaction with the membrane. So which one is the correct structure of the dimer, left or right?
The right one, the purple one.
Yes, the right one is the correct. Does everyone understand? If we have this kind of dimer, all its surface will be hydrophilic, the red amino acid. So if it's hydrophilic, it cannot interact with the membrane. Okay?
So does that mean in this question, if we want the monomer to be hydrophobic, it means it has to be the beta turn that has the hydrophilic inside and hydrophobic outside?
No. The beta sheet, it's like a plane.
Yes.
Okay.
So the monomer structure. So what is the structure for the monomer?
The monomer structure is a beta sheet. Indeed, the isolate monomer, when they say the isolate monomer is hydrophobic, it means that one part of the monomer is hydrophobic. In my side view, the top side of my side view, it's hydrophobic, right? So you have one part which is hydrophobic and one part which is polar. I don't know if I answer your question.
Yes, thank you.
Okay. Other question? No? So last exercise. Okay. So you know the prion proteins? It's the proteins involved in neuronal degeneration disease as the Creutzfeldt-Jakob disease. Okay. And in these prion proteins, you have two conformation. One is healthy, and it's called PRP. And one is pathogenic, which is called PRPSC. Okay? So you have two conformation, one healthy and one pathogenic. Okay? So in this exercise, we investigate about the secondary structure of the protein PRTC and PRPSC by infrared and CD. Okay, so you have the infrared band spectra here. So the nature of the variation vibration, I'll give you the answer because it's not quite important. It's the CO stretching band. Okay. And why we record this spectra in D2O? It's because of the transparency window. And because in water, H2O, you have a band in the same region that sorry. That the one of a amide one bond. Okay, so here it's the amide one band corresponding to the CO stretching. Okay, so how we can obtain the percentage of each secondary structure? So it's a mathematic treatment, so it's the deconvolution. And what is the major secondary structure for each protein? So, for example, for the dot line, it means the PRP. Let's see. The maximum is here. So it's 1,630 centimeter minus 1. For the dashed line in here, pick another color. It's 165 around. And the last one will be this sunlight one. 1,660. Okay. So if you let's see if I can take the table. Okay. Sorry. No. Where is it? If I take the table of my slide, okay. You have this. So the PRPC which has a maximum at 1660, it's an alpha helix in majority. And for the two other, so in violet, it's PRPSC. You have one bond, which it's correspond to the random core. Here. Another red conformation, okay, and the other at 1600, sorry, 30 centimeter minus 1, each correspond to a beta sheet. Okay, and then if you see the CD spectra, you have two minimum. One, two. So it corresponds to the alpha helix. Okay, so this corresponds to the PRPC proteins. Okay, so if we see, excuse me, yes. Can you see the slide of the prion?
Yes.
Yes. So you have in the prion from alpha to beta, when you are healthy, your protein, the prion protein, are very rare conformation change. It means here you have the alpha, the alpha helix conformation is the healthy proteins, and the beta sheet conformation correspond to the pathogenic proteins. So in the case you are still healthy, you have very rare conformation change. But if you have infection seeding, you will have change in the conformation. So you will have an equilibrium between the alpha helix and the beta sheet. So if you know you have PRPC here and PRPSC here, okay? So you will have interaction between the beta sheet of the PRPSC and the PRPRC. The interaction between both proteins induce another conformational change of the PRPC. So you will have a lot of PRPSC. So you will have a lot of sheet interacting together, and you will obtain what we call amyloid. And this is amyloid, which is responsible of the neurodegenerative disease. Okay? Okay. So this is the end, yes, of my lecture for today. Except if you have question, I can answer. Or if you have question, we can, for the exercise, maybe you can do it again by your own and tell me if you understand the exercise. Okay?
Okay.
Okay. Are you still there?
Yes.
So see you next week. And I will finish my lecture about protein structure. Okay, we will see the tertiary structure and the quaternary structure, and we have a lot of exercise. Should I send you the exercise and you can prepare them? Maybe, no? No?
Yes, maybe you can
Maybe.
send me first so
Okay.
we can prepare.
I will tell you which one you can prepare, okay? Because you can, okay? I will send you the slide of the exercise and about the lecture. Bye. See you next week.
Bye. Thank you so much for the lecture.